So we're going to go through a few more heat engines, and you might recognize a few names from the University of Glasgow. So the first one we're going to talk about is the Stirling engine and Stirling cycle. And the Stirling cycle is the closest one to Carnot. Carnot cycle is completely reversible. Now, when you start going into details of thermodynamics, the highest efficiency that you typically get in any thermodynamic process are for the processes that are most reversible. The point about this is that a reversible process typically has got very low loss or no loss at all. So if there's large losses in a system, it's unlikely to be reversible. So Robert Stirling was a theology student in the University of Glasgow in the early 19th century. And he used to go along to natural philosophy lectures where many of the scholars of the day used to teach thermodynamics and the early days of thermodynamics. He, in his spare time, came up with the concept of the Stirling engine and how to use it for practical thermal conversion systems. There are uses of Stirling engines. I'll show you some. Probably the biggest use is actually in nuclear-powered ships and nuclear-powered submarines. There's not so many of those about. And the real problem with the Stirling engine is that whilst it is a practical cycle, the reversible heat exchanger, the regenerator, is actually very difficult to make and make efficient. The higher the pressure you go to in the systems, the easier it is to make it efficient. High pressure systems are more dangerous, they're harder to engineer, they're more expensive. So you'll see later we talk about the Rankine cycle, and I'll explain why the Rankine cycle is used more in thermal power stations. So there's basically two forms of Stirling engines. There's the two-cylinder version, and there's the one-cylinder version. And in this case, you've got the hot side. You basically get heat going around and being pumped from one side to the other. And you basically have a heat exchanger that exchanges the heat between the two cylinders. In the one-cylinder version, the heat exchanger is really in the section right between the two. And what you're trying to do here is that the gas that you have in the system will absorb heat, in this case at one cylinder, and then it will give the heat to the other one to expand. And that basically creates the reversible system. And because it's reversible, it gives you the highest efficiency. Now, it's not quite up to the Carnot efficiency. There are going to be losses in here, particularly in this heat exchanger. It's not going to be 100% efficient. There'll always be some heat lost, conducted in the system, because you can never have thermal conductivity of 0. But it's the closest you get to the Carnot cycle. When we look at the cycle, we'll go through and show you, at least for the two-cylinder variety. This is sort of shown with the heat exchanger much more explicit in the center in this particular diagram. So in our pressure versus volume diagram, you want to think the whole way through about Boyle's law when we talk about this. So pressure times volume equals constants times temperature. So if we go from 1 to 2 and we have heat going into the system, this is being done in an isotherm. So we basically have T as constant, which means that if the pressure decreases, the volume has to increase to keep PV as a constant. So this is why between 1 and 2, you can see this going down as the volume increases, so that PV is a constant in the system. As P reduces, the heat going in the cylinder here is basically absorbed. Now, for most of the applications, you'll have your boiler and you'll burn your fuel, and the heat comes in at that point to the gas and gets moved around the cycle. And this is the closed cycle part. Typically, it's actually gases in here rather than liquids that you see in Carnot and Rankine cycle. So now if we look at 2 to 3, the piston moves the gas down to the cold end. And in doing so, we get to the point that some of the heat gets moved out of this expansion cylinder and moved over to the cold cylinder. It will end up being absorbed by the regenerator, and some of that might be thrown out, but you'll see at the end what the real basis is to make this a very high efficiency process. So in this case, the regenerator is absorbing the heat as it gets pumped towards the colder cylinder in the system. So it's a constant volume. So what we have is, as the pressure reduces, it also means that the temperature reduces, and so we have to have heat being removed from the system, and that's being absorbed by the regenerator in the center of the device here. So if we look at the isothermal compression, here what we've got is the momentum of the flywheel between the two cylinders. Because we've had expansion, the cylinders are going to move around, get pulled around. So this is how we're going to have our work done being extracted from the Stirling engine. Because the volume is reducing, it means because of PV equals nRT, this is isothermal, so T is a constant. So PV is a constant. It means that as the volume reduces, the pressure has to increase in the system. And then for the final part in Q2, so from 4 to 1 here, as the gas expands in the regenerators releases the heat into Q1. So that goes back into the system, and that allows the expansion to start again and to move around in the particular system. So here what we've got is that the volume is constant. So Q1 has to be absorbed since the pressure has to increase in the system to allow us to maintain the PV equals nRT between 4 and 1 in the system. Now, ideally, what we want to happen here in the regenerator is that, in fact, Q2 moves around and ends up inputting as the Q1 going in here. So this is what is perhaps a little bit confusing in how when we go around this diagram, but in fact, we absorb the heat and then we release it again. So we're absorbing the heat. So we show to start with the heat gets put into the regenerator and then it's put back in the phase diagram from this side. So in effect, we want the regenerator to move the heat, extract it from here and put it back in over here after the isothermal compression in the system. And if you get the lag, that thermal lag I spoke about earlier, correct, with the momentum of the flywheel going around, this works extremely well and you get the recyclable system. So you can see here that we're extracting heat out and then we're putting heat in. Provided there's no losses in this, we get extremely high efficiency and very close to the Carnot cycle. So there have been many examples of this shown. This is one looking at a very sustainable and renewable energy, taking solar and using solar to actually do the heating and using the Stirling engine to convert the heat from the solar energy into electricity. So it was a European research project. The actual solar farm and systems were tested in Spain. So we'll talk about solar, both solar thermal and photovoltaics in a later lecture. But as you can imagine, if you can go to sunnier climes than Glasgow, the ability to generate large powers increases quite substantially. Now, this particular system, you can see there's a large concentrator that takes the solar light. It focuses it down onto the Stirling engine. This is the Stirling engine here, and the solar radiation goes onto this part to provide the input heat going into the Stirling engine. So this concentrator concentrates the light by a factor of 2,500. It's an 8.5 meter diameter reflector here, and it gives about 9.2 kilowatts net output power. So the conversion efficiency is 16%. So that doesn't seem that high, and it's much lower than some of the high numbers that we saw when we looked at the Carnot efficiency on large delta T's of about 700 degrees C. And that's simply because with this solar system, even with the concentrator, the maximum temperature we can heat up this hot part of the Stirling engine is limited to a few hundred degrees C. And so that's what actually gives us the low efficiency here. It's the delta T we can create in the system is limited because of the solar collector and the ability to concentrate light and heat up from that process. So it's an expensive technology. It's well below the theoretical efficiencies. A lot of the problems here are really trying to increase the temperature you can get on the hot part of the Stirling engine and collect more energy from the solar radiation. Okay, entropy. So we're going to talk for the rest of the lecture. We need to talk about entropy to be able to understand some of the thermodynamic cycles for power stations. Entropy is a very difficult concept for many students and for many professors to understand, for that matter. There is a classical way of defining it, and there's a much more modern statistical mechanical way of defining it, and I'm going to give you both. The change in entropy is something that classical thermodynamics could define. Entropy is defined as the number of ways of a system may be arranged. You can think about it as the degree of disorder of a system. So for instance, if we consider water and the entropy of water, if we have water frozen, so it's ice, that's got the least amount of disorder, and so that actually has the lowest entropy. If we look at water as a liquid, that's got a higher amount of entropy than ice because it's got a higher degree of disorder, since the atoms, well, the molecules of water H2O can actually move around, and that gives more disorder, it gives more entropy. If we go to a gas, so if we heat up H2O water to high enough temperatures, we create steam, the entropy increases even more. And in doing so, well, basically because we go to a gas, in the gas, the atoms or the molecules move around much more quickly, and that's much higher levels of disorder compared to a liquid. So the entropy increases again. But what is typically used in a lot of thermodynamics is the change in entropy is the reversible change in heat divided by the temperature you have for the system. So this is what we'll use later on. You can think about this in different ways. It's quite a difficult concept to take up. There's a more modern definition that's come from statistical mechanics, and this also relates directly into information, because entropy and information are actually equivalent from a thermodynamic perspective. So statistical mechanical definition of entropy is the number of different ways we can arrange a system. So let's say we've got an atom, and these are the energy levels in an atom. And if we put an electron into the atom, just one electron, the electron potentially could actually be in any of these other microstates. Now, it's most likely and statistically most likely to be in the lowest energy one, but you can calculate the probability that it's going to be in higher energy states. And for any of these states, I, the probability of it being in that state is I. So the entropy is defined as minus Boltzmann's constant. So this is 1.38 times 10 to the minus 23 joules per Kelvin. And then the total entropy of the system is the summation of all the probabilities of being in the ith microstate times the log of being the probability of being in the ith microstate. So what we can think about is there's a finite probability of that electron being in one of the higher energy states at any time. That probability increases the higher the temperature of the system, and so the entropy of the system increases as we increase the temperature. So that's two different ways of looking at entropy. This is really what we need to know for this course and what we'll use throughout the rest of the lecture. Okay, so before we look at the Rankine cycle, we want to look a bit more at water and steam and what goes on with water and steam and the phase change as we move from water to steam. So this is the temperature versus entropy diagram of the water steam system. So we're not going to look at ice in this, but that would be another one and further down in this. We get something that looks like this. And what we're interested in is that if we heat up the water and it's at a particular pressure from the atmosphere, so let's assume that everything is just in a pot on a cooker, and in your kitchen, if you're doing that, the atmosphere is at atmospheric pressure. So the water will heat up until it gets to 100 degrees C. And then what happens is that you get a phase change going on where some of that water starts to evaporate and become steam as the phase change goes on, and the water is basically absorbing the latent heat to allow vaporization of the water molecules into steam. We then get this period as the water boils away and you get steam coming out of the pot. If you were to put a lid on and make that a closed cycle system, you'll have both water and steam inside the pot. So even if you start with a system that there's no steam in there to start with and no volume of air, you would end up creating some steam, and actually in those cases probably the pressure is going to increase as well. What we're assuming in this is that the pressure remains constant across this line. Once we get to this point C and all the water has turned into steam, then we get to a regime that's called dry steam. So if we've made the pot with a sealed lid and all the water turns into steam, we actually have only steam, and it's what's known as dry steam in the system. Now, as I've said, water going along here, we get to this point, we get to 100 degrees C. If I choose a line that's higher up this diagram with higher temperatures, if I increase the pressure, I can increase the boiling point of water. So what this tells us thermodynamically is if I increase the pressure, I can increase the boiling temperature for water, I can get a higher temperature. And this is simply, again, looking at Boyle's law and PV equals nRT. If I have a constant volume and I increase the pressure, the temperature has to increase in the system. So this is how the boiling point of water increases. For a constant volume, I only have to increase the pressure. So what's good about this when we think about the Carnot efficiency is that you want high temperatures to get high efficiency. So if I increase the pressure of any of these steam cycles, I could increase the temperature, I could increase the conversion efficiency of the steam engine just through the Carnot efficiency. So this regime here is called the superheated regime, and it's above the boiling point. So we also want to be in this dry steam region because we can increase the temperature of the steam to be greater than the boiling point of water. So the combination of the two, we want to be operating our power station in this regime up here because we can get the highest temperatures, and in getting the highest temperatures, we should be able to get the highest efficiencies and the highest powers. Now, there's a complication. And when we go through the Carnot cycle using this diagram, you'll see what that is. But we want to be operating in the dry steam regime up here not just to actually get the highest temperatures available, but because if we have water vapor around, we have water in itself in this mixed water and steam regime, what we get is we'll also have droplets of water when it's used in turbines. And those droplets of water can damage the turbine blades. And that means that you need to do a lot of maintenance. You actually have to replace the turbine blades every few months if you're operating in this regime. And Rankine was the one who really came up with a way to prevent this from happening. And that we'll talk about the Rankine cycle a little bit later. So let's look at a bit. This slide is a bit of a diversion. It's going to allow you to do one of the tutorial questions, but it's a concept that's very useful when you work with steam engines or if you're working with steam in power stations. So it will seem a little bit contrived to start with, but when we get to the end of the slide, hopefully you'll see the value of the approach and what you can do with it. So if we've got the total mass of water and steam in a system, so the total mass is going to be the mass of the fluid plus the mass of the gas. Now, if we're at low temperatures, that will just be water. If we're at high temperatures, it will just be steam. If it's somewhere in the middle, then it's going to be a mixture of both the liquid and the gas. And we can define the volume in the same way. The total volume of the system is going to be the volume of the fluid plus the volume of the gas. And we can write this in terms of specific volume, which is just the total, well, the absolute volume divided by the mass. And we can rewrite this to be the mass of the fluid times the specific volume of the fluid plus the mass of the gas times the specific volume of the gas. And the specific volume of the water and steam in total is the absolute volume, or the total volume divided by the total mass. Well, the total volume we've defined up here through this equation. We can just put this in here. So it's the mass of the fluid times the specific volume of the fluid plus the mass of the gas times the specific volume of the gas, divided by the total mass of the system, so just the mass of the fluid plus the mass of the gas. Well, we can rearrange this equation by putting this in, and on this side we can have the total mass minus the mass of the gas. So that's just making the mass of the fluid equal total mass minus the mass of the gas that moves over to the left-hand side here. And so we've just exchanged there. If we now divide here to get 1 minus the mass of the gas divided by the total mass times the specific volume of the fluid plus the mass of the gas divided by the total mass times the specific volume of the gas, you can see what we've now done is actually got the same parameter on this side of the equation. So we can define a variable which is just the mass of the gas divided by the total mass. Now, okay, that maybe doesn't seem so great. What we've done is the mass of the gas divided by the total mass, and we've got an equation for the specific volume equals 1 minus this parameter x times the specific volume of the fluid plus x times the specific volume of the gas. But the strength of being able to do this is that we can measure this mass of the gas and the total mass of all the water that gets put in the system in the first place. So we can determine x for any boiler system or steam engine that we make.
Can you please explain me the second step, that is volume V is equal to V of F plus V of G, that is equal to MF VF plus MG VG?
Sorry, what, this bit?
No, the second step.
That one?
No. Volume is equal to V is equal to VF plus VG. That is equal to MF VG plus MG VG. Above.
What here?
No. That line, volume is equal to V is equal to VF plus VG. It's a second step in the slide. Bullet point number 2.
There.
This, yeah, sir.
So this is just by the definition. So the total volume of the system is the volume of the fluid plus the volume of the gas. The definition of specific volume is the absolute volume divided by the mass. Okay?
Okay.
So if we turn this around, this capital V equals small v times m. So it's just taking this m up to there. And then we do that for the fluid. So we get the mass of the fluid times the specific volume of the fluid. So this specific volume equals the total volume of the fluid divided by the mass of the fluid. And it's the same for the gas. Do you understand that now?
Yeah.
Okay.
Yeah.
So we've got this specific volume. If we write out the enthalpy and the entropy, we can write them in the same way. And it allows us to actually understand what percentages we have of the fluid and the gas in terms of the enthalpy and in terms of the entropy in the system. So while it might seem a little bit contrived to get there, what it allows us to do is if we can determine X here as the mass of the gas divided by the total mass of all the water and steam in the system, and that's just the mass of the water we put in at well below 100 degrees C, then we can determine the enthalpy and the entropy, and we can also determine how much is in the fluid and how much is in the gas. And we can do the same for the entropy as well. So this is a very useful trick that's used for people that design boilers and power stations to be able to do a lot of different thermodynamic equations and understand powers and so on. So there's a question that you will see in the tutorials that you need to use this in a particular example. Right, so let's look at the Carnot cycle. So a key thing I said when we went through the Carnot cycles before is that what Carnot did was that he set the internal energy changes to 0. So what that means when we look at this temperature versus entropy phase change diagram with water and steam and dry steam, you cannot cross the boundaries, because to do that, we're going to have a change in delta U going on. So you can only run Carnot inside a fixed boundary. And what we have is we have the compressor, and the work done on the compressor to actually will increase the temperature from cold to hot and actually doing that. We input heat, and in inputting heat, we actually increase the entropy of the system. What we're actually doing here is we're increasing disorder, and the volume goes up if we end up, well, we'll be at constant pressure. So, sorry, let me start again on that. So that the volume basically can increase in the system, but since you fix the volume, you end up with the molecules of the steam actually moving, or the molecules of water and steam moving faster, which allows you to get the velocity you need for the turbine to turn it. When we look at the turbine, it's extracting the kinetic energy out of the system. It does work, or it extracts the work done from the turbine out of there, which comes out here. We go down to a condenser. The condenser will recover some heat, Q2, taking heat out of this to condense all the steam into water. In fact, in the Carnot, it doesn't condense all the steam into water. There's still going to be some steam left before you go back and run the compressor cycle again. So there's a number of issues around this. And the first one is we cannot operate the boiler in the dry steam region. So we cannot get a very high temperature compared to if we could get into this part of the phase diagram. So therefore T1 is reduced, and for a given cycle, we end up with reduced efficiency. As I said before, we've got water droplets in here. Those water droplets can damage the turbine blades, and that can create a lot of problems. So we need to find a much more practical cycle that we can run the turbines only in this dry steam regime. And this is what Rankine came up with. So the initial Rankine cycle is this cycle. So you can see Carnot only had the whole cycle inside this water and steam regime. You were not crossing these phase boundaries. But in Rankine, he's basically got it set up so that you can have an internal phase change and ultimately get into the dry steam regime. So we've got a compressor at F. We compress, we get to point A. We're going to have our heat going into the system. That allows us to do the phase change. We can get into the dry steam regime. So we do a superheat that takes us from B to C. So we need an additional heater here to put more heat energy into the system. And then we go through a turbine where we start at least in the dry steam regime. We've got a condenser. We can extract heat out of the system. And then we can start again with a compressor and go around this whole thermal cycle. So we've got our work going in the compressor. We've got the work done coming out of the turbine. We've got the heat. In fact, we've got multiple heat stages. We've got the first one here, and then we're going to have multiple, the phase change, and then the dry steam regime as the superheat up the top. And then we extract or recover heat out the system down the bottom. Now, the problem as this is drawn at the moment, and just having one superheat stage in the Rankine cycle, is you still have problems of some water droplets down here that can damage the turbine blades. But there's a fix to get around that, and we'll show that in the next slide. So now what you do instead, so that you always have turbines operating only in the dry steam regime, is that you run one turbine, and then as you get close to this phase boundary where you might get water droplets, you reheat the system. So you get a reheat going on, you then have another turbine, you have another reheat, so you heat back up, and then another turbine. And if you do this enough times and get far enough out here, you can end up not having any water at all when you're actually using the turbines. And this is what runs in modern thermal power stations. Coal, nuclear, not gas. That we'll explain the gas cycle a little bit later today. So you can see that a lot of things have been changed. It allows us to get to much higher temperatures than if we just ran Carnot. We've also got heat going in as phase changes as well. So let's just go around a Rankine cycle power station, and you can see some of the parameters in running a modern power station. So here we've got the work done in the pump, the work done in the compressor. So we take water in at a fairly low pressure, and at constant temperature, what we're seeing going on is that the pressure increases. So in PV equals nRT, the temperature is constant. P is being increased by putting work into the pump. We then have the boiler, and we've got the heat energy going in the first boiler. And that increases the temperature of the steam quite significantly. Well, it creates steam, it does the phase change, and then we get into the superheat regime. These will go into different turbines. First, a high pressure turbine. There'll then be a reheat, go into an intermediate pressure turbine, a reheat, and then going into a low pressure turbine. So in each case, you're moving through the different parts of the Rankine cycle and extracting the work done to a Faraday generator to generate electricity. The steam comes out at a lower pressure and you run it through the condenser, where you'll typically have a heat exchanger and a cooling loop, and you'll extract Q2 heat energy out of the system. Now you can see here some of the parameters. This is using 200 tons of coal per hour. In terms of water, there's 1,800 tons of water per hour. But in terms of cooling water, just for the condenser, there's 56,000 tons of cooling water per hour. So it gives you an idea of the scale of a large coal-fired power station. Right, this is an appropriate time for the final break in questions. So I'll just stop the recording.